All right, folks, get ready for a wild ride, because today we are taking a deep dive into a research paper that's, well, let's just say it's a bit of a brain twister.
I'd say that's putting it mildly.
The title alone is enough to make your head spin. Quantum Hyperfluidic Oscillations in Post-Neometric Lateral Displacement. A comprehensive analysis of pseudo-causal anisotropic metrics.
Yeah, it's a mouthful, but trust me, the concepts behind all that jargon are actually pretty mind-blowing. Once you get past the terminology, it's really fascinating stuff.
Okay, so let's try to break this down. First up, quantum hyperfluidic oscillations. I'm picturing like some sort of cosmic lava lamp, but with, quantum stuff instead of lava.
That's not a bad analogy. We're not talking about actual fluids here, but the way these quantum formations behave is kind of similar to how liquids flow and oscillate. It's like a cosmic dance of quantum structures, constantly shifting and interacting.
Okay, so there's a pattern to this cosmic dance, even though it's happening at a level we can't even see.
Exactly. And that's where the post-neometric part comes in. We're dealing with phenomena that are beyond our current ability to measure. It challenges our whole understanding of the universe as we know it.
So we've got these quantum structures flowing and oscillating in ways we can barely even imagine. What happens next?
Well, that brings us to post-neometric lateral displacement, which is where things get really strange.
Okay, I'm intrigued. Hit me with it.
Imagine objects not just moving through the 3 dimensions we're used to, but shifting in ways that defy our current understanding of space and time.
So they're like sidestepping into dimensions we can't even perceive.
You got it. Movement, but not as we know it. And this throws a wrench into traditional physics because it suggests there are dimensions and movements beyond anything we've ever observed.
Okay, now that is a game changer. So our current models of physics can't account for these movements.
Nope. And that means we're missing a big piece of the puzzle. This research suggests that reality is far more complex and stranger than we ever imagined. And it gets even weirder when we bring in gravispheric waveform bifurcation.
All right, you've definitely got my attention. What in the world is gravispheric waveform bifurcation?
Think of it this way. We all know about gravity, right? It's what keeps our feet on the ground.
Yeah, pretty familiar with that one.
But imagine that gravity in these uncharted dimensions has the power to behave in ways we can't even fathom.
Gravity's going rogue. This is getting good.
Now add waveform bifurcation to the mix. This suggests that gravity's influence can actually split, creating ripples that could potentially form entirely new realities.
Hold on. Are we saying there could be multiple realities branching off from our own because of gravity going wild?
It might sound crazy, but that's what this research is pointing to. It could completely revolutionize our understanding of, well, reality itself.
Okay, my brain needs a minute to catch up. We've gone from quantum structures dancing in hidden dimensions to gravity potentially creating new realities.
Yeah.
This is definitely not your average physics lesson.
And we're not done yet. This is where it gets really interesting, because now we have to talk about flux-bounded synaptic harmonization.
Now, synaptic usually makes me think of brains and neurons. Are we suggesting these quantum structures have some sort of consciousness or something?
Well, that's a fascinating thought, but not quite what we're getting at here. In this context, synaptic refers to the connections within these quantum fields. Think of it like a complex web of interactions between these structures, all governed by certain limitations and boundaries, hence the flux-bounded part.
So even though these quantum structures are doing their own thing in hidden dimensions, there are still rules governing how they interact with each other.
Exactly. And understanding those rules could be the key to unlocking a whole new level of control over these mind-boggling phenomena.
All right, so we've got quantum structures flowing, shifting dimensions, potentially creating new realities, and they're all connected in a complex web of interactions. But what does it all mean? Where does this research lead?
That's the most exciting part. This research is paving the way for what scientists are calling holomorphic engineering.
Holomorphic engineering. Sounds like something straight out of Star Trek.
It kind of does, doesn't it? But it's the real deal. We're talking about the ability to engineer reality itself, harnessing the power of these quantum phenomena to manipulate matter and energy at their most fundamental levels.
Hold on, we're talking about manipulating the very fabric of reality. What kind of implications are we talking about here?
We're talking about the potential to create materials with properties we can only dream of, develop entirely new forms of energy, and push the boundaries of technology in ways we can barely imagine.
Okay, my mind is officially blown. This is truly revolutionary stuff, and we've covered a lot of ground already. I'm sure our listeners are eager to hear more. But before we dive deeper, let's take a quick pause to let everything sink in.
Indeed. It's not every day we get to ponder the possibility of engineering reality itself. We'll be back in a moment to explore the potential applications and implications of this groundbreaking research. Welcome back. Before the break, we were talking about holomorphic engineering and how it could revolutionize our world.
Yeah, it's still hard to grasp, to be honest. We're talking about actually engineering reality, right?
It sounds like science fiction, I know, but what makes this research so remarkable is that it goes beyond just theory. They actually did experiments to test their ideas.
Really? So they weren't just messing around with equations?
Oh no, they used incredibly advanced equipment to actually observe these quantum effects.
Wow, what kind of equipment are we talking about here?
Well, for example, they used something called a multi-phase oscillometric analyzer.
Oh, that sounds like something straight out of Star Trek.
It does, doesn't it? But this device allows them to measure those tiny fluctuations and oscillations of these quantum structures, and in multiple dimensions, too.
So they can actually track these movements into dimensions we can't even see.
Yeah, it's amazing. And their findings really back up their theories. One of the biggest discoveries was related to post-Neometric lateral displacement. Remember, that's the idea of those quantum structures shifting into hidden dimensions.
Right, like they're doing the side shuffle into another reality.
Exactly. Well, their measurements showed that these shifts were way more pronounced than anything predicted by traditional physics.
So they're finding evidence that our current understanding of physics is incomplete, that there's more to the universe than we thought.
Absolutely. It's like they're opening a window into a whole new realm, a realm that we never even knew existed. And they're finding a whole new set of rules governing how things work there.
Incredible. Did they find anything else to support their theories about these quantum structures?
They did. They found a really fascinating correlation between the decay of those quantum structures and something else we talked about, gravispheric waveform bifurcation.
The whole gravity splitting, creating new realities thing.
That's the one. It seems like there's a deep connection between those quantum events and the very fabric of space and time.
So the death of these tiny quantum structures could lead to the birth of new realities.
Wow. It's a mind-boggling concept, right? It suggests that even tiny quantum events can have a huge impact on reality as a whole. But of course, the researchers acknowledge that they're just scratching the surface here.
So what's next? Where do they go from here?
They've outlined some really interesting directions for future research. One thing they want to do is develop more sophisticated mathematical models.
To help them understand how these structures behave in those hidden dimensions.
Exactly. It's like they're trying to create a map for a place that we can't even see.
That sounds like a pretty tough challenge. How do you map something that you can't even perceive directly?
It's definitely not easy, but they're confident they can start to understand these phenomena better by refining their current models and incorporating new mathematical tools.
So it's like trying to solve a giant puzzle where you can only see a few of the pieces.
A very complex puzzle. Another key area they want to focus on is refining their models for predicting how those quantum connections, the synapses, behave.
Right, because those connections have certain limitations and boundaries, don't they?
Exactly. They believe that if they can study those limitations more closely, they might be able to figure out how to actually control those connections.
So they're not just trying to understand these structures, they're thinking about how to actually manipulate them. That's where things get really interesting. And maybe a bit scary too, right?
It's true. The potential implications of this research are huge, both positive and potentially negative. If we learn how to control these quantum connections, who knows what we could achieve? But we need to be very careful about the possible consequences, too.
That's a good point. We're talking about potentially engineering reality itself. There could be all sorts of unintended consequences. But let's stay positive for now. What are some of the potential benefits of this research? What kind of real-world applications could it lead to?
Well, the possibilities are pretty mind-blowing. We were just getting to that. Imagine materials, but design at the quantum level. Materials with properties we can barely even dream of right now.
Like what? Give me some examples.
Okay, picture substances that are super strong, but so light they're practically weightless. Or materials that conduct energy, but with zero resistance.
Wow. That could revolutionize, well, everything. Construction, transportation, energy.
Absolutely. And that's not even the half of it. What if we could actually tap into the energy of these quantum oscillations? We could have clean energy, sustainable energy, enough for everyone.
Yeah, no more fighting over oil.
Yeah.
Okay, that all sounds incredible, but let's get back to the nitty-gritty of the research for a minute. The paper mentions something called Subderivative tensor stratification. I gotta be honest, I have no idea what that even means.
It's definitely a mouthful, but it boils down to this. They're trying to develop even more advanced mathematical models.
To map those hidden dimensions.
Exactly, to predict how those quantum structures behave in those dimensions we can't even see. It's like creating a GPS, but for a place that's totally beyond our perception.
So if we can map this uncharted territory, does that mean we're closer to actually controlling these phenomena?
You got it. And that's where things get really interesting. They also talk about something called hyperadaptive waveform node modeling.
Okay, now you're just making words up.
I know. It sounds complicated, but basically they're looking at ways to refine the models they use to predict how those quantum connections, those synapses we talked about, actually behave.
So it's like they're trying to understand the language of these quantum structures.
A perfect way to put it. If they can figure out how these connections evolve and interact, they might be able to manipulate those interactions too.
This is all pretty mind-blowing stuff. It's amazing that we're even starting to understand these things, let alone talk about manipulating them.
I agree. It's pretty incredible. And the potential applications are huge. The researchers even suggest that these techniques could be used to map synaptic discontinuities, but in real time.
Wait, you mean actual connections in the brain?
It's one of the possibilities they're exploring. Imagine being able to actually see how information flows through the brain at the quantum level. It would revolutionize everything we know about consciousness, memory, maybe even neurological disorders.
Wow, so we've gone from talking about these tiny quantum structures in hidden dimensions to maybe unlocking the secrets of the human brain. That's quite the journey.
It is, isn't it? It just shows you the amazing potential of scientific inquiry. We started with this one research paper, and look where it's taken us.
Absolutely. It's a testament to human curiosity and the power of asking questions. This has been an incredible deep dive. It makes you wonder what other mind-blowing discoveries are out there, just waiting to be uncovered.
It really does. There's so much we don't know about the universe, but that's what makes it so exciting. Every new discovery opens up a whole new world of possibilities.
Well, on that note, I think it's time to wrap things up for today. We've covered a lot of ground, from quantum fluids and hidden dimensions to the possibility of engineering reality itself. It's a lot to take in, but hopefully it's inspired our listeners to keep exploring and keep asking questions.
And who knows, maybe one of our listeners will be the one to make the next groundbreaking discovery in this field.
That's what we love to hear. So until next time, keep exploring, keep questioning, and keep wondering. The universe is full of mysteries, and we'll be here to guide you through the most fascinating ones.